Okay, AP Calculus 6.3, integration or anti-differentiation by parts. All right, let's start with the reminder of the product rule. Product rule, if you were taking d dx of uv, that would be equal to u dv dx plus v du dx. Remember, that's u v prime plus v u prime, all right, the product rule. All right. Now, if I were to take the integral of both sides of this equation, all right, then I would have the integral of d dx of uv dx, okay, equals the integral of u dv dx plus the integral of v du dx. Okay? So notice a few things can happen here. First of all, here I'm taking the antiderivative of the derivative. So we know from the fundamental theorem of calculus, part 1, that that just gives us the original function. So for here, this is going to be equal to uv. Okay? Now, when I take the derivative of the antiderivative of this, before I do that, I can cancel these dx's out. So I end up with the integral of u dv, and the same thing can happen here. So I would have the integral of v du. Okay? Now, I can rearrange that so that I end up with the integral of u dv is equal to uv minus the integral of v du, and this is our formula right here for integration by parts. Okay? Now, how does this work? Well, let's start with an example. Okay? My example is going to be, so this is example 1. Okay? The example is going to be looking for the integral of x cosine x dx. So as I've said before about antiderivatives, we don't have formulas for antiderivatives in the same way that we have formulas for derivatives, because we are essentially undoing derivative formulas, okay? But this formula here is an exception. So in order to use this, we need to take our x cosine x and we need to separate it into two things, into a part that we're going to consider to be u and a part that we're going to consider to be dv, okay? Now, the part that we're going to consider to be u, we want that to be something that is easy to differentiate and that simplifies when you differentiate it. And the dv, we're going to want to be something that is easy to anti-differentiate. Okay, so my choices are going to be this. I'm going to let u equal x, and I'm going to let dv equal cosine x dx. Okay? So now that I've done that, okay, du would be equal to dx. Okay? And v would be the antiderivative of this, okay, which is sine x. So now I have all that I need to fill in this formula, okay? I need uv, and then I need to be able to take the integral of v du, and I have all of that. So my uv is going to be x sine x, okay? And then I'm going to subtract the integral of v du, which would be sine x dx. And lo and behold, this is something that we know how to anti-differentiate, okay? So my answer is going to be x sine x minus the antiderivative of sine x, which is negative cosine x. And of course, because this is an indefinite integral, we're going to have a plus c, all right? So my answer would be x sine x plus cosine x plus c. So this is the solution to this indefinite integral, okay? Don't believe me? Take the derivative of it. d dx of x sine x plus cosine x plus c, okay? Now, this is going to be a product rule, so it's going to be u times v prime, which is cosine x, okay? Plus v, which is sine x, times u prime, which is 1. And then the derivative of cosine x is minus sine x. And of course, the derivative of a constant c is 0. So look what happens here. I get x cosine x. So the derivative of this is this. So that means that this must be the antiderivative of this. Okay? And that is integration by parts. That's a very simple example. Okay? So what I want you guys to try right now is I want you to try number 1 and number 3 from the textbook. Okay? Why don't you pause this video and then try to get an answer, and then you can check your answer in the back, and then when you come back to watch, I'm going to go through the solutions. Okay? Great. Okay, so now we're going to look at problems 1 and 3 in the exercises from section 6.3. Okay, problem number 1 is the integral, the indefinite integral of x sine x dx, which is very similar to the example I just did. It's just sine instead of cosine. So our u is going to be x, and our dv is going to be sine x dx. Okay, now that means our du is going to be dx, and our v is going to be the antiderivative of sine x, which is negative cosine x. Okay, now remember our formula. The integral of u dv is equal to uv minus the integral of v du. Okay, and we have everything we need here. Uv is going to be negative x cosine x, okay, minus the integral, and v du is going to be negative cosine x dx. Okay, so we're almost there. Okay, this is negative x cosine x. Okay, these negatives can cancel, so I'm going to have plus the integral of cosine x dx, and we know that that is sine x, so the answer is negative x cosine x plus sine x plus c, because it is an indefinite integral, okay? And if you want to check it, find the derivative, you will find that the derivative of this is x sine x. All right, now number 3. We have the integral of 3t e to the 2t dt. Okay? So my suggestion, first of all, let's pull the 3 out. All right? It's just in the way. So we've got t e to the 2t dt. Okay? Now, both of these have derivatives that are fairly simple, but the antiderivative of t is going to be t squared over 2. So it's actually getting more complicated. So we want to make that equal to t. So if u equals t, all right, and we're going to let dv equal e to the 2t, okay? So that would mean that du is equal to dt, and v, then you have to think about this a little bit. All right, remember that the derivative of e to the 2t would be 2 e to the 2t. We want the antiderivative of this. So we're going to have to take care of the 2 that's in there. Now you could do a quick u substitution, but I'm just going to skip that. I'm going to go right to it. If my dv, I'm sorry, it would be e to the 2t dt. My antiderivative of this would be 1/2 e to the 2t. And the reason for that is, if I were to take the derivative of this, then it would be e to the 2t times the derivative of 2t, which is 2, and that 2 would cancel with this half, and I would get that. Okay? So now I have everything I need. All right? So once again, the formula, the integral of u dv is equal to uv, I'm sorry, not an integral. It's going to be equal to uv minus the integral of v du. So I fill in what I have. uv is 1/2 t e to the 2t. And then minus the integral of v du. v du is going to be 1/2, and I'll put that out here, e to the 2t dt. All right, now I already told you that the antiderivative of e to the 2t is 1/2 e to the 2t. So that means our answer is going to be 1/2 t e to the 2t minus 1/2 times 1/2 e to the 2t, all right? And then plus c, so in the end we end up with 1/2 t e to the 2t minus 1/4 e to the 2t plus c, okay? And that is the indefinite integral. Oh, I did forget something. What did I forget? Somebody tell me. You don't know? I'll tell you what I forgot. I forgot my 3. So that means that I have to have a 3 outside of all of this. All right? These things happen. As long as you catch it, it's okay. So in the end, I would have a 3 here. All right, so I would end up with 3/2 t e to the 2t minus 3/4 e to the 2t, and then I don't have to have 3c because c could be any number, so I'm just going to make it plus c. So that is going to be our indefinite integral to this, okay? Okay, section 6.3, example 2. In this case, we're going to use repeated use. We're going to have repeated use of integration by parts, okay? Which can seem like a lot. There is going to be a shortcut to this that I'm going to show you called tabular integration, all right? But first we have to understand how this all works. So for example 2, our problem is going to be the integral of x squared e to the x dx, okay? Now, as I said before, you want to pick your u to be something that differentiates and gets simpler, and you want your dv to be something that the antiderivative, if it doesn't get simpler, at least it doesn't get more complicated. So that having been said, let's make u x squared, and let's make dv equal e to the x dx, okay? So then du would be 2x dx, okay? And our v is just going to be e to the x, okay? Because the derivative of e to the x is e to the x. That's what's so wonderful about e to the x. So remember our formula once again. The integral of u dv equals uv minus the integral of v du. So we're going to fill in what we have. uv is x squared e to the x. That works out nice. But now we're looking at the minus the integral of v du, and v du is going to be 2x e to the x dx. And the problem with this is that now I've got x e to the x, so I've got a product again. So I'm going to have to do integration by parts twice. But you know, you're already an expert at integration by parts, so you do it once, you do it twice. Why not? Okay? So once again, I'm going to pull the 2 out. Let's try not to forget it this time. All right? If I forget it, make sure you remind me. All right? So this is what I'm going to be looking at here. So I'm going to let my u equal x, and I'm going to let my dv equal e to the x dx. So then du would equal dx, and v would be e to the x. Okay? So then once again, I use my formula, I fill it in. So I've still got this x squared e to the x. I'm not forgetting my 2. And then now I have to do integration by parts. So it's uv, which would be x e to the x, okay, minus the integral of v du. So minus the integral of e to the x dx. And to my great relief, this is something that I know how to get. So I'm not going to have to do it a third time. Twice is enough, okay? So that's going to give me x squared e to the x minus 2x e to the x plus 2, and then the antiderivative of e to the x is e to the x, 2 e to the x plus c, of course. So this is my answer, all right? Now, before I go on, I want you to look at this. And you don't have to say anything yet, but try to think if you see some kind of pattern that's developing with this repeated integration by parts. You got x squared, you got 2x, you got 2. Something's happening there, all right? So when we learn the shortcut of tabular integration, whatever's happening there is going to come into play, all right? So just kind of keep that in the back of your mind, all right? I want you to do problems 5 and problem 7 from the textbook, and then I want you to go and check your answers in the back of the textbook. And in the interest of time, and of not repeating myself over and over again, I'm not going to go through them on the board here, but if you can't get the correct answer, all right, then you need to contact me. Either comment on the classroom or send me an email and we'll figure it out, okay? And I'm going to go right on to example 3. Now example 3 is, we're doing the same thing, but it is what we would call an initial value problem. So we're going to be looking for an antiderivative, but we're going to be looking for a particular solution based on being given an initial value, okay? So we're going to start with the differential equation, and that equation is dy dx is equal to x ln x. Okay, and then our initial condition is going to be the point 1, -1. So what that means is that the value of y at 1 is going to be -1. All right, and as you know, with an initial condition, for a solution with a differential equation, we can actually get a real solution where we don't have a c involved. Okay. So to start, of course, we know that our y, okay, our actual function is really the indefinite integral of x ln x dx. Okay, so when I'm going to choose my u and my v, okay, x always makes a very good u. Class is not dismissed. X always makes a very good u because it gets simpler. It becomes just 1 when you take the derivative. And then, but in this case, that's not going to work because this would make an absolutely horrible dv. So I'm reassessing here. So what we're going to do is I'm going to let u equal ln x, okay? And then I'm going to let dv equal x dx, okay? Because even though that's not ideal, it would be better than having to find the antiderivative of ln x. I mean, we can get it. You could look in your book and find it, but that's not going to make things easier. So then our du, well, what is the derivative of ln x? It's 1 over x. So du is going to be 1 over x dx, okay? And v is going to be 1/2 x squared, all right? Because the derivative of 1/2 x squared is x. So there you go. All right, so uv is going to be 1/2 x squared ln x, and then we're going to minus the antiderivative, the integral of v du, which is going to be 1/2. I'm going to leave that outside here, okay? And then x squared times 1 over x dx. All right, now it turns out I can put the x squared over the x and cancel, so I would end up with the integral of x dx, okay? Which is easy enough, I know how to do that, so I end up with 1/2 x squared ln x minus 1/2 times 1/2 x squared, okay, plus c. So these are all equal to y. All right, so then that is going to give me, let's see, 1/2 x squared ln x minus 1/4 x squared plus c. So this would be our indefinite integral for this, okay? But we're given an initial condition, okay? Which means that we can put these values in for x and for y into this equation, and we can come up with a value for c. All right, I'm going to erase this and I'm going to do it over here because I'm running out of room. So once again, my y is equal to 1/2 x squared ln x minus 1/4 x squared plus c. Now, because of the initial condition of 1, -1, that would mean that -1 equals 1/2 times 1 squared ln 1 minus 1/4 times 1 squared plus c. What's ln1? It's 0. So that means this whole thing is 0. Okay, which means that -1 equals -1/4 plus c, and that means that c is equal to -3/4. So that means that my particular solution with my initial condition is going to be 1/2 x squared ln x minus 1/4 x squared minus 3/4. And that's the answer. Okay? I want you to try number 11 and number 15 and see how that goes. And then we'll be back in a minute. Okay, we're going to look at example 4 now, which is one of my favorite examples in all of AP Calculus. We're looking for the indefinite integral of e to the x cosine x dx. Okay, so we'll let u equal e to the x. We'll let dv equal cosine x dx. So du would be e to the x dx, and v would be sine x. Okay, so then my uv would be e to the x sine x, and minus the integral of v du, which would be e to the x sine x dx. So far, so good. Of course, like the last problem, I'm going to have to do another integration by parts. So once again, I'll let u equal e to the x, and I'll let dv this time would equal sine x dx. Okay, so that would mean that du equals e to the x dx, and v would now be equal to negative cosine x. Okay, so don't forget that you still have this. Okay, so e to the x sine x minus, okay, and then we're going to have another integration by parts here. So it's uv, which would be negative e to the x cosine x, minus the integral of v du, which would be the integral of negative e to the x cosine x dx. Okay, now if I go and I straighten all this out, get rid of all these negatives, okay, I would get e to the x sine x plus e to the x cosine x, and then I have minus of a minus of a minus, so it would be minus the integral of e to the x cosine x dx. So essentially what I'm saying here is that the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x minus itself, minus the integral of e to the x cosine x. So what have I done? I've just gone around in a circle and I haven't accomplished anything. So do I just give up? Do I just pretend that this is 0? No, there is a way. And it's a beautiful solution. Imagine that I added this guy right here to both sides of the equation. What I would end up with is 2 times the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x plus some c. All right? But I'm not looking for 2 times the integral of e to the x cosine x dx. I'm just looking for this. So how do I find it? Well, go back in your mind to pre-algebra, 6th grade or whatever. If you had 2x was equal to something and you wanted to figure out what x was, you would divide both sides by 2. So therefore, our answer is going to be, and I'm going to write it over here, is going to be that e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x divided by 2 plus c. So there you have it. All right, another way to write that, you could say it's 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. There you have a beautiful solution to what seemed moments ago to be completely impossible. All right? So that's example 4. Okay, so we're going to go over tabular integration, but before I do that, I want you to go to your textbook to the exercises and try numbers 17 and 19 and look the answers up. Make sure you're doing them correctly, all right? Let me know if you have any problems, all right? Now, example 5, tabular integration. So tabular integration is a shortcut for when you have repeated integration by parts. And I want to go back to example 2, where we were looking at the integral of x squared e to the x dx. So remember when we did that integral, we did an integration by parts, but then we ended up with the integral of x e to the x. So we had to do it a second time. And if you recall, the solution to this was actually x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And when we got the solution, I asked you to look for a pattern and try and, just think about it, to hold on to it, not say anything to anybody, but just hang on to it. And, we were going to come back to it. So hopefully you found a pattern. And the pattern that I was hoping you would see is that, so here's your u. Well, remember that u is the part that we use differentiation on, that we take the derivative of. So the derivative of x squared is 2x. Now here we have negative 2x, all right? But 2x is there, right? And then the derivative of 2x is 2. So really you've got u, you've got negative u prime, and then if you took the derivative of that, this would be negative of u double prime. Okay? Well, not really. It would be positive of u double prime, but it would be negative of that primed. Okay? So, and then e to the x. Now, it's hard to see the pattern as much with e to the x because we're taking antiderivatives of e to the x, but antiderivatives and derivatives of e to the x are just e to the x, so it doesn't change. But really what's going on is that this is an antiderivative of this, and this is an antiderivative of this, because that's what we do with e to the x. So to start, we're going to change things up. We're going to say let f of x equal x squared, okay? And g of x equal e to the x. Now, if it helps you, you can still think of them as u and v, okay? Or u and dv, really, if that helps you. But we're just going to name them as two different functions here, okay? And when we did integration by parts, this function was one that we took derivatives of, and this function was one that we took antiderivatives of. So I'm going to make a table. So I have x squared here, and I've got e to the x here, all right? So I start with x squared. I take its derivative, it's 2x. I take the derivative of 2x, it's 2. I take the derivative of 2, it's 0. Remember, with polynomials, as you continue to take derivatives, they get simpler and simpler. And this is a method you're going to use when one of your parts is a polynomial, okay? Because eventually it gets down to 0. If it doesn't eventually get down to 0, then integration by parts is not going to work because it'll never end. It will just go forever, and nobody wants that, all right? Now, antiderivatives of e to the x are e to the x, and e to the x, and e to the x, and so okay? So, so notice our solution here, all right? So the first term is x squared e to the x. That is this times this. And I'm going to put a little plus here because it retains the sign of x squared, okay? E to the x, all right? Then the next term is going to be 2x e to the x, but I'm going to put a little negative here because it changes its sign, okay? Then I'm going to have 2 e to the x, that is positive again, and then the next one would be 0 e to the x, which is just 0, so we're done. So that's how we get this, and that is our tabular integration, all right? I'm going to look at one more example. This is example 6. Example 6, we're going to take the integral of x cubed sine x dx. Okay? Now, I think it would be obvious to have our derivative come from the polynomial, x cubed, and our antiderivative come from our trigonometric function, sine x. Okay? So, we start with x cubed, we go to 3x squared, okay? We go to 6x, we go to 6, we go to 0. Okay? Derivatives, right? Now, starting with sine x, the antiderivative of sine x. Don't make the mistake of doing the derivative. It's antiderivatives on this side. The antiderivative of sine x is negative cosine x. The antiderivative of negative cosine x is negative sine x. The antiderivative of negative sine x is negative cosine x. And the antiderivative of negative cosine x, the antiderivative of negative sine x would be cosine x, and the antiderivative of cosine x would be sine x. Let's make sure that's right. Sine x, antiderivative is negative cosine x. Antiderivative is negative sine x. Antiderivative is cosine x. Antiderivative is sine x. Okay? So you got to watch your signs here, your plus and minus, okay? So here we go. This one's plus. This one's minus. This one is plus. And this one is minus. So in the end, our answer is going to be negative x cubed cosine x. Okay? Now it's minus of a minus, so it's plus 3x squared sine x. Then it's plus 6x cosine x. I'm running out of room. Okay, then it's minus 6 sine x. And of course, don't forget plus c. Okay, so let me write it down here so everybody can see it. Negative x cubed cosine x, because it's negative cosine x times x cubed, and it's positive of that. The next one is negative of negative 3x squared sine x, so it's actually positive. The next one is positive of positive, okay? Plus, are you sure about that? Yes, I'm positive. 6x cosine x, and then minus 6 sine x, and then plus c. So there you go. That is example 6, tabular integration. Now, if I did this without tabular integration, I would have to do integration by parts 3 times, all right? Which I would not want to have to do. Even I would not want to have to do that, and even I would probably screw it up somewhere along the way. So it's nice to have the tabular form, okay? Now I want you guys to try number 21 and number 23 on your own. Check the answers in the back, see how you do, okay? I have a couple more examples from this section, all right, that involve inverse trigonometric functions and logarithmic functions. Okay, example 7. We're going to use integration by parts to find the indefinite integral of the natural log of x. Okay, now I know that you're saying to yourself, how can we use integration by parts when there's only one part? Well, there isn't one part. There's ln x and there's dx, and that's what we're going to use. All right? So now you may recall from a previous lesson not long ago, we actually were given the solution to this, and we just had to use a derivative to show that it was indeed the solution. But I told you that getting the actual solution was something that we were not ready to do yet. Well, we're ready to do it now because we know how to do integration by parts. All right? So I'm going to let my u be ln x. And I'm going to let my dv just be little old dx. All right? So that means that du is 1 over x dx. And my question for you, if dv is dx, what's v? All right? Well, what's the antiderivative of a constant? It's x times that constant. Well, here the constant's 1, so v is equal to x, right? The derivative of v equals x would be dv equals dx, all right? So we're going to set up our integration by parts here now. uv would be x ln x, okay, minus the integral of v du. Now v is x, so it would actually be x times 1 over x dx. Okay, so I have x ln x minus the integral. Now x over x is 1, so it's minus the integral of dx. All right, and you're saying, well, what's that? Well, I just told you what it was. It's x. All right, so my answer is going to be x ln x minus x plus c. And if you recall from that example that we did, okay, that is what the indefinite integral of ln x was. That's what it is, all right? We found it using integration by parts, okay? Now, example 8, we're going to solve an initial value problem, okay, for a differential equation. And what we're actually going to find is we're going to find the antiderivative of arc sine x. So dy dx is equal to inverse sine of x. Okay? And we're going to find the particular solution for this that goes through the point 0, 0. Okay? So I'm going to use a similar method that I used to this. I'm going to say, let's let u equal inverse sine of x, and let's let dv equal dx. Okay, so du, do you guys remember what the derivative of arc sine x was? All right, I do. It's 1 over the square root of 1 minus x squared, the dx. Okay? And v, of course, as I said in the last example, v is x. All right? So once again, we're finding the solution to this integral. Okay? So our uv is going to be x inverse sine of x. Okay? And then our minus the integral of v du is going to be minus the integral of x over the square root of 1 minus x squared dx. Okay? And I know you're saying to yourself, well, that doesn't help me out. But it does, because we know how to do this, because we studied integration by substitution in the last section, and that's what this is going to use. We're going to let u equal 1 minus x squared, and then du is going to be negative 2x dx. So then negative 1/2 du is going to equal x dx. And lo and behold, that's what we have right here. Okay? So, this is going to be x inverse sine of x minus negative 1/2 the integral of u to the negative 1/2 du. Okay? Because this is my u, it's to the negative 1/2, and negative 1/2 du is equal to x dx, so I have everything taken care of there. Okay? So this would be x inverse sine of x plus 1/2. Now the antiderivative of u to the negative 1/2, you add 1, so you would have u to the 1/2, so the square root of u. Okay? So it would be the square root of u divided by 1/2, which is times 2. So it would be times 2 square root of u. Now u is 1 minus x squared. Okay? And then that would be plus c. I think I have everything here. I'm going to check. Because, yes, we're good. So then this is going to be x inverse sine of x, and then the 1/2 and the 2 cancel, so plus square root of 1 minus x squared plus c. So this here is actually the antiderivative of arc sine x. Okay, it is the indefinite integral of arc sine x, and you know, were you to look that up in a textbook or something, this would be what they would give you. Okay, so that's good to know, right? You could always check it, all right, by taking its derivative. I'm not going to do that right now, but you could do that, and you should get back arc sine x. Okay, now I'm going to move over here because I need a little more room. We're going to just find a value for c that makes it go through the point 0, 0. So we have y equals x inverse sine of x plus the square root of 1 minus x squared plus c, and then we know that 0 is equal to 0 times inverse sine of 0 plus the square root of 1 minus 0 squared plus c. So obviously this is going to be 0. Okay, this is going to be the square root of 1, which is 1. So we end up with 0 equals 1 plus c. So to me that means that c equals negative 1. So our final solution would be y equals x inverse sine of x plus the square root of 1 minus x squared minus 1. And there you have it. And that is the end of section 6.4. I hope you enjoyed this video lesson. In the next lesson, we're going to look at, I'm sorry, that was not 6.4, that was 6.3. In the next lesson, we're going to do 6.4, which is a great section. It's very important. There's always a lot of problems on the AP test dealing with exponential growth and decay. So we're going to learn separation of a differential equation. We're going to learn the law of exponential change. We're going to learn about half-life and compounding interest and Newton's law of cooling. And we're going to learn about bald-faced hornets, which I know you're excited about. We're going to learn about carbon dating, which in this time of quarantine may be the only kind of dating that we're allowed to do. So, you know, it's all very important stuff. All right, thanks for tuning in. There is an assignment being posted. Take care, wash your hands. all right? And I hope to see all of you very soon.